Hey folks, today we're going to take a look at the IPv6 address space. IPv6 addresses cause a great deal of confusion for a lot of networking professionals. Let's take a few minutes and walk through a quick explanation of how IPv6 addresses work. Then we'll take a look at a few examples, and we'll go to the IANA website and actually see where IPv6 address space is defined within the context of networking. These slides come from Training City's IPv6 hands-on workshop. They make up a small part of the class, which is mostly hands-on focused, with captures of IPv6 traffic using the protocol analyzer Wireshark. In this particular module, we'll take a look at a few of these points in our short YouTube video. So today we're going to try to develop a fairly complete understanding of the IPv6 address structure and be able to recognize and expand or shorten IPv6 addresses. We'll talk a bit about IPv6 subnetting as well. So the first thing to know when you discuss IPv6 addresses is that the address space itself is 128 bits, not 32 bits, which we're all familiar with in IPv4. Address assignments are managed by the Internet Assigned Numbers Authority, just like they are with IPv4. In fact, if you think about IANA, their role has to do with, amongst other things, all numbering that we use within the Internet or effectively within TCP/IP. Whether it's the assignment of IPv4 and IPv6 addresses globally within the Internet to regional Internet authorities and then onward to Internet service providers and ultimately to you, it's also the assignment of port numbers. For example, you may know that port 80 is a well-known port number used with Hypertext Transfer Protocol. It's IANA that decides that port 80 will be used for Hypertext Transfer Protocol. They do the assignments for types of Internet Control Message Protocol. All the things you can think of that have to do with numbering, you can learn about at the IANA.org website. So back to IPv6. We need to understand, or we will understand in the main training class, that there is a much more extensive implementation of multicasting in IPv6 than what we experience now, or what we did experience with IPv4. Instead of being a kind of afterthought, multicasting in fact is a normal part of how IPv6 operates right on your LAN. There are other aspects of how IPv6 changes the way you think about address space and layer 3 networking. For example, the relationship with relating to a layer 2 Ethernet address is different. There's no more ARP. Instead of using ARP, we'll find ICMP messages in use. And we'll see that there's a great advantage of using ICMP instead of ARP, where ARP messages travel directly over Ethernet and therefore are not really feasible to encrypt or authenticate. ICMP messages, on the other hand, travel over IP. We can implement IPsec, which is a mandatory part of IPv6, and now encrypt and or authenticate all of our layer 2 address relationships. Many other things we'd explore in the class, of course. We won't see broadcast IPv6 addressing anymore. We'll see multicasting. The IPv6 addresses, when we look at them, are not written in dotted decimal. They're written in hex. So if you weren't comfortable with hex numbering before, now is the time to get up to speed on how we use hex numbers. The most important thing to remember when we talk about hex generally in computer science is that we use hex numbers to represent 4 bits. So, for example, the hex number F relates to the binary number 1111. We choose to have the hex number 0 be represented by the binary equivalent 0000. Of course, the direct relationship is 0 binary equals 0 hex, but there's nothing wrong with saying 0 hex equals 0000 binary. And it's that relationship that we use when we discuss hex numbering in networking. That is to say, every hex number from 0 to F will represent some combination of 4 zeros and ones. We group our IPv6 addresses into 8 16-bit or 4 hex number, what we call blocks. Subnetting is done in the first 64 bits of an IPv6 address. The last 64 bits of the address we'll see are used as a local address field, something that we can map, for example, the MAC address into. So when you think about an IPv6 address, it's very useful to think of it almost as two numbers. The first 64-bit value, which will help us to find the subnet, and the last 64 bits that'll help us to find the unique interface ID. So 128-bit address separated into 8 16-bit hexadecimal numbers. And here's an example. We see 4 hex numbers, 4 hex numbers, and if you were to add this all up with each of these hex numbers representing 4 bits, you would see 128 zeros and ones in binary being represented here. So for example, this 0 hex is representing 0000 binary. This F is representing 1111 binary. You can get more details in RFC 4291, and there's a link provided here directly to the RFC. So 4 hex numbers and a colon, 4 hex numbers and a colon. 1, 2, 3, 4, 5, 6, 7, 8. 8 of these blocks. Think of the first 4 blocks as helping to define the network that your IP address is part of, or the subnet, and the last 4 blocks providing the unique interface ID for this particular IP address. So for example, your home network may start with these 4 blocks, and then each machine on your network might use these 4 blocks. When we think about IPv6 addresses and MAC addresses, they're both written in hex. You just kind of have to get used to it. The dotted decimal notation of IPv4 is simply not used. It's not practical to use with such a large address. As a result, it isn't so easy to remember IPv6 addresses. Many of you are comfortable now remembering 192.168.1.1 or 99.3.7.2, and you sort of learn to remember the actual IP addresses of devices in your network. That's really not feasible anymore, just like you can't really remember the MAC addresses. So again, off the top of your head, you probably know the IPv6 address of your home, IPv4 address of your home router, but you probably will never know the IPv6 address of your home router as something that you've memorized. Okay. As a result, we rely more and more on namespace as opposed to address space when it comes to finding devices on the LAN, things like DNS. We explore a variety of namespace options in the hands-on class. So just to reiterate, your IPv6 address has 1, 2, 3, 4, 5, 6, 7, 8 blocks. Each block represents 16 bits and is separated by a colon. If you can remember this, you're well on your way to understanding the basic structure of an IPv6 address. Also, think about the IPv6 address in 2 parts. The first 4 blocks, and then the last 4 blocks. We'll find the first 4 blocks generally speaking, assigned through our internet service provider, or most of these first 4 blocks, and the last 4 blocks being defined locally by the device or perhaps using DHCP. So here's an example of a IPv6 address again, and we see the blocks. Now, when it comes to IPv6 address notation, the most important rule to remember is that there is a colon after every 16 bits, that is to say after every, if you like, 2 bytes, or another way to express that would be there's a colon after every 4 hex numbers. With IPv6, the designers of this address scheme have decided, or did decide, to create some methodology for shorthand in the display of IPv6 addresses. There's a couple of shorthand gotchas that you just need to memorize and practice. In Training City's hands-on TCP/IP or IPv6 class, we go over these examples numerous times. We do paper labs on them. We do lots of captures of these packets, and you come away with a very solid understanding of this shorthand notation. Let's go quickly through it here in the video. There are 2 core rules. Leading zeros in each of the 8 blocks can be omitted. So for example, if a block contains 4 zeros, the 3 leading zeros can be omitted. Secondly, all zeros in between 2 colons, if a block contains all zeros or multiple blocks contain all zeros, can be shortened to 2 colons. Let's take a look. So here we see an IPv6 address, 2001. These zeros cannot be omitted because they're not leading zeros in a block. :0. In this example, there would be 3 zeros in front of this 0. They can be omitted because they're leading zeros. :13FF, so that block remains in its full display. :09FF, we could drop this 0 if we wanted to, and that would be :9FF. :0, again, there would have been 3 leading zeros. Again, drop 3 leading zeros. Again, drop 3 leading zeros. And in this case, we could drop these. These could all be dropped to be :1. So here we see this address shortened a bit more. 2001 :0 :13FF :09FF. That 0 could be dropped. Now we see 2 colons representing these 3 blocks. And then we see the last block shortened to a 1. So not entirely shortened. There is 1 extra 0 here which could be dropped. We'll do that in a moment. This may bring up another question, which is, why don't we put in 2 colons here and 2 colons here? Our rule only allows us to put in double colons once in an IPv6 address. And the rationale is that if we had double colons here and double colons here, and we gave this address to somebody, they wouldn't necessarily know where all of the 0-filled blocks belong. How many blocks are there of 16 bits in an IPv6 address? Do you remember? 1, 2, 3, 4, 5, 6, 7, 8 blocks of 16 bits. You must remember that there are always 8 blocks of 16 bits. The reason you have to remember is that when you see the double colons, you have to count backwards. There must be 8 blocks, but I only see 1, 2, 3, 4, 5. Because I see 5 blocks, granted they're missing the leading zeros, but I see, or some of them are, I see 5 blocks, 1, That is a block, 4 zeros. The 0 tells me there's a block, one block there. So 1, 2, 3, 4, 5. If I see 5 blocks, and I know there has to be 8 blocks, this would represent 3 blocks of 4 zeros each. 1, 2, 3. There are a couple of special addresses. There's a number of special addresses we'll explore in the training class. Colon, colon, which is in effect, if you like, all zeros. Colon, colon, and the number 1. This would be 7 blocks of zeros, and then 0001 loopback address. You could try, for example, to ping colon, colon, 1 if your IPv6 software is running. And just like pinging the loopback address in IPv4, you'll get a response from your own interface card. So we have a little exercise we would normally do in the class and try to shorten these addresses. Let's try to do one here during the training class. Let's take a look at this address, 2300, followed by these additional blocks. Let's begin by making sure that we actually see 8 blocks. 1 block, 2, 3, 4, 5, 6, 7, 8 blocks. Each one has 4 hex numbers in it. Therefore, each one is 16 bits. 16 times 8 is 128 bits. So this is an IPv6 address. Now, how could we shorten it? Well, I see a lot of zeros here, a lot of zeros here, here, and here. Could I do double colons here and double colons here? What do you think? No, I can't. I can use double colons to shrink either this or this, but not both. Why not? Because if you gave that address to somebody with 2 sets of double colons, they might know how many blocks are missing, but they won't know where they belong. So let's imagine we use double colons to shrink 1, and the other we shrink to 0, colon, 0. Now we have 2300, colon, colon, 3455, colon, 0, colon, 0, colon, 4522, colon, A489. You can try the other ones if you like. We do lots of examples in the training class. So, here's the other possibility. You receive an address that's already been shortened. What do? Let's take a look at the first address, 2600, colon, colon, 5. How many blocks of 16 bits, or 4 hex numbers, should there be if we were looking at a fully expanded version of this address? Do you remember? That's right, 8 blocks. But I only see 2 blocks, 2600 and colon 0005. I see 2 blocks. There has to be 8 blocks. Therefore, how many blocks are hidden by the double colon full of zeros? 6 blocks of all zeros, 4 zeros, 4 zeros, and so on, and then ending with colon 0005. Okay, that was a quick introduction to IPv6 addressing. Next time we'll take a look at how IPv6 subnetting works. Thanks and have a great day.